As we start off chapter 4, working the problems, it's important that you have these at reference. So we've talked about these transition metal ions that you need to memorize the charge. You need to be able to tell which ones are type 1, that is, there's only one possible charge for ions, or the ones that have multiple charge ions. Those are type 2. It's also important that you know all your polyatomic ions by their name, their chemical formula, and their charge. Again, this is the list that I will use for tests. There's maybe a few more on homeworks, but use the polyatomic ion list on the homework site when you're doing homeworks if you don't find it on this list. All right, digging in. The first question is asking us to give the empirical and molecular formula, and it gives me a structural formula. Again, definition, the empirical formula is the lowest ratio of elements formula. And then the molecular formula is the chemical formula that has the actual number of each element atom. So first we have to do an accounting. Now with a structure this big and this complicated, sometimes using like a colored pen or a pencil may be helpful. I'm going to use my highlighter. I'm going to start with my carbons. I'll put them over here. This will be carbon. All right, ready. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, double check. I think we've got them all. So we have 12 carbons. And let's see, we have hydrogen. We'll do hydrogen next, and then we'll do oxygen. All right, for hydrogen, we'll pick another highlighter color. Let's do orange. All right, hydrogen, there's a lot of them. 1, 2, 3, because there's 2 of them. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. I think I've got them all. 22. And one more, we'll do green for the oxygen. All right, let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, I think I've gotten everything in there. Okay, and in this particular case, to go to, this would be the molecular. Sorry, molecular. To do the empirical, I have to see, can I divide all subscripts by the same number? So at first it looks like I could do 2. 12 is divisible by 2 and 22 is divisible by 2, but 11 is not. This is as low as it gets. So in this case also, the empirical formula is C12H22O11. However, had it been something like C12H22O12, that would have reduced to C6. Let's do if. It wasn't that, but C6H11O6. So that's not what the problem asked, but just to show you what's the difference between a molecular and an empirical formula. In the second question, it's asking me to draw Lewis models for cesium, cesium ion, nitrogen, nitrogen ion. And actually the ions are fairly helpful in this case because once I see it, it's very easy to see what it's going to do as a predictable ion. Cesium is group 1. So that means it's going to have 1 valence electron. Nitrogen is group 15. It has 5 valence electrons. And remember, we're going to put the symbol, cesium, and then we're going to put the dot on one side. There's only one. It doesn't matter which side it is. I should have one side has 1 dot. 3 sides have 0 dot. But it doesn't matter which side I had picked. All right, so as an ion, it's clear that this is going to be losing all valence electrons. That's group 1 and group 2. All lose all their valence electrons. So I'm going to lose it, which means I will have 0, but that's going to make it, because it's missing one, it's going to make it have a plus charge. All right, the next one is nitrogen. We draw N as the symbol, and we're going to put the electrons around it. So it's 5 valence electrons. I can do 1, 2, 3, 4, 5. Again, any solution in which I had 3 sides have 1 dot and one side has 2 dots would be acceptable. I add up to 5, one side has double dots. It doesn't matter which side has the double dots. Okay, so again, I can see clearly this is a nonmetal. It's going to gain electrons to get a full valence. In this case, it's not a period 1 element, so that's going to be 8 electrons. And I can see it needs 1, 2, 3 for all the sides to be paired up. So it's going to gain 3 electrons. And when it does so, all the sides are going to be filled up. However, it will now have a charge. It gained 3 electrons, so it's going to have a 3- charge. So these are Lewis models for the various ions and their atoms. All right, now we dig straight into naming and writing formulas. When I see a naming question, the first thing I need to see is, 1, is it ionic, covalent, or acid? Remember, acids are going to start with H. It's more complicated than that, but in this course, we're just going to say formulas that start with H. Covalent is going to be 2 or more nonmetals. And ionic is going to be a metal and a nonmetal. Or if there's any polyatomic in it, then it's ionic as well. So I could have a polyatomic ion and a nonmetal, or a metal and a polyatomic ion, or a metal and a nonmetal. I have lots of options. Okay, the second question is, if it is ionic, I need to identify the cation and the anion. If it's covalent, then I'm going to be naming the species based off of their subscripts. The subscript would be as a prefix. Okay, so in this case, I see that iron is a metal. There we go. And oxygen is a nonmetal. So with a metal and nonmetal, so this is ionic. So I need to identify my cation and anion. Remember, the cation always comes first. There's only 2 elements, so this has to be my cation, and my anion has to be, but those are not the charges. Now I have to decide on the charges. Okay, so iron's tricky. Iron is type 2. So I can't just memorize its charge, because it's sometimes +2 and it's sometimes +3. So instead, I'm going to focus in on my anion. I know that oxygen always must be 2-. Because it's 2- and there are 3 of them, I can see I have a total of 6-. And I have 2 irons. So I know that this must be 6 plus. Well, the only number that's divisible, 6 divided by 2, this would be each have to be 3 plus. Okay, having figured that out, now I can name it. The way we name anions, if they are type 2 metals, it's the element name and the charge in Roman numerals. Wow, I don't know why this is messing up so much. And the anions are named as the element name with the "ide" ending. Okay, so for this, it would be iron. Because it needs the Roman numerals charge, I figured out that it's +3. 1, 2, 3. And then oxygen, but I'm going to change the ending to "ide." Okay, the second one. I see sodium is a metal. And this is a polyatomic ion. Even if I wasn't sure, I know that sodium's a metal. It must be ionic. It's not hydrogen. It's not a nonmetal. It's starting with a metal. It must be ionic, which means the other part has to be a polyatomic because it's got more than one element in it. It's got polyatoms. So at that point, I'll have to identify it. So the way that we name our cations that are metals, I first have to identify if sodium is +1 or, is type 1 or type 2. So as I write these down, I'm going to determine what their charges are. Sodium, always, it's group 1, so it's always +1. This is going to be a type 1. And for the polyatomic, I have to go look at my sheet and look it up. This is 3-, and it's called phosphate. No, because it has a reserved name, that is how I name it. So I already have the ending name. I just have to go back. For a type 1 metal, it is only the element name. I don't need any charge. So this would be sodium phosphate. All right, we'll continue on with the next ones. This is a bunch of writing formula. Again, first I want to identify, is it ionic or covalent? If it's ionic, I want to find cation and anion, and then use a method to find subscripts that get me a neutral charge. What? That get neutral charge. And then I have to clean it up. Because normally I have to write the ion charges in temporarily. I may put subscripts of 1. All that needs to get cleaned up. If it's covalent, I'm going to use the prefixes to determine subscripts. And if it's an acid, I'm going to find the anion and then use H plus for cation. Even though it is covalent, we can get the answer right if we treat H plus as the cation, and then repeat the process as we do for ionic. Find the subscripts for neutral charge. Okay, so I see that this is a metal. So this is ionic. I also see that this is a charge. That also tells me it's ionic. So I have 2 indicators. Let's continue on the other ones. Zinc, again, this is a metal. 8 and ite are indicative of polyatomic ions. So I see a metal, I see a polyatomic ion. This is ionic. Aluminum, this is a metal. This is ionic. Copper is a metal. I have a charge. I have an 8 ending. That's a polyatomic ion. So this is ionic. Calcium is a metal. 8 is a polyatomic ion ending. So these are ionic. So all of these are ionic. And that is step 1. So at this point now, we can practice doing the rest. I'm going to change pens. Let's go with a red. Okay, the first thing is I kind of want to separate and find my, the 2 words are going to separate. What is my cation? What is my anion? So this is my cation. This is my anion. And again, okay, so there are 3 types of cations. Metals, they would just have the metal name. Metals that are type 2, they have the metal name and the charge in Roman numerals. Or polyatomic. Well, the real one we really need to worry about is ammonium. So this is clearly a metal type 2. So I have my charge because it's given to me as the Roman numeral. When I'm looking at the anion, there are 2 types. Either it is a nonmetal element or it is a polyatomic. This has the "ide" ending. It is not a polyatomic, so it's going to be sulfur. And then I have to look, it's group 16, so it has 6. It's going to make a -2 charge. So now I have my 2 ions. I'm going to move them over here. Fe, 3 plus, S, 2 minus. Now the way I have to do this, so I usually do the crisscross method. I am looking for subscripts that when I multiply the charge times the subscript, and I don't consider the sign, I just consider the absolute value of it, that I get the same for both ones. Note that one way to do it is I need something that I multiplied 3 by to get the same number as I multiplied 2 by some other number. Well, if I just crisscross, I'm guaranteed to get the same number. So I'm going to put a 2 here, and I'm going to put a 3 here. So note that 3 times 2 is 6, and 2 times 3 is 6. So I have the same number. I have one's going to be positive, one's going to be negative. They're going to cancel each other out. So this would be my formula. However, I need to clean it up. No ion charges and no subscripts of 1 and no parentheses if the subscript outside the parentheses is 1. So in this case, this becomes Fe. I'm just going to remove my ion charges. 2s3. Okay, zinc nitride. Again, I see that there is no charge, but this is a metal, so it's simply going to be a type 1 metal. I do need to know its charge. At this point, I have to go to my list because it is not group 1 or group 2, so I have to look at it, but it is always 2+. Nitrite is a polyatomic ion. I have to look at the polyatomic ion list to see that this is NO2 with a -1 charge. Once again, I can do Zn2 plus NO2 minus. Really, this is like a 1 minus, so I'm going to crisscross. This will be a 1. Crisscross, this will be a 2. I need to put parentheses around it so I can separate the 2 that's part of the polyatomic ion from the 2 that's the subscript of how many polyatomic ions I have. So 2 times 1 is 2, and 1 times 2 is 2. This is balanced, but now I'm going to clean it up. I'm going to get rid of the ion charges, and I'm going to get rid of the subscript of 1. All right, the next one, aluminum nitride. So this is a metal. It's clearly a type 1 metal because there's no charge given. So it's aluminum. I have to look up what its charge is. For aluminum, it's always 3+. So this ending is telling me that this is just a non-metal anion. It is not a polyatomic anion because the non-metal anions, the ones that are simply made of a non-metal, all have the IDE ending. So this is nitrogen. I have to look it up. It's group 15. That means it's going to be a 3- charge. So one way to do this is to recognize 3 plus, 3 minus. They are already balanced if I have one of them. But if you didn't notice that, we can still use the crisscross method. So if I crisscross down and crisscross down, I see that 3 times 3 is 9 and 3 times 3 is 9. So I have equal numbers of charges of positive and negative. However, these can be reduced. We always need to reduce them down to the lowest ratio. So they can, by this case, I can divide them both by 3. So this becomes 1 and 1. Which means when I rewrite it, these are now not 3 but 1. I don't keep subscripts of 1. I don't keep the ion charges. So cleaning it up, it's just ALN. Copper 2 chlorate. Copper 2, this is a type 2. The nice thing about type 2s when we are going to formula is I don't have to even look it up because it tells me my charge right there. The downside is that when I'm naming it, I have to figure out the charge. And then chlorate, this is a polyatomic ion, ClO3 minus. Double checking that one. It's not as familiar to me. I'm 90% sure. ClO3 minus. Yes, it is. All right, so now I can simply do my crisscross. Cu2 plus, ClO3 minus. So I need 2 here, and I need to bring this is an implied 1. I need to bring that down to here. So I'm going to have 1 copper and 2 chlorate. Again, I'm going to get rid of the charges. I'm going to get rid of the subscripts of 1. And I'm going to get ClO3, 2. Calcium sulfate. This has no Roman numeral, so this is a type 1 metal. Okay, so this would be calcium. It is group 2. That's a 2 plus. And sulfate is a polyatomic ion. I have to go find its formula, SO4 2 minus. Once again, you might notice that the 2 plus immediately cancels out the 2 minus, and I just need one of each, and I can get to calcium sulfate. Or I could do 2 plus SO4 2 minus, and I crisscross 2 and 2. I have 4 and 4, but these can be reduced to 1 by dividing both by 2. And so I have one of each. I'm going to take away the ones. I'm going to take away the charges. And because the subscript outside the parentheses of the polyatomic is 1, then I get rid of the parentheses as well. So CaSO4. If you had noticed right away, 1 and 1 works, you would have saved some time, but you still get there if you use the crisscross method, as long as you reduce. Write the formula of dinitrogen pentoxide, write the formula of sulfur dioxide, and carbon tetrabromide. Okay, so at this point, remember the first step is it a ionic, covalent, or acid? And when I'm looking here, I see that this is 1. I see the di. Also, I see N is a nonmetal. And I see the pent. And I see this is oxygen is a nonmetal. So this one is covalent. I see sulfur and oxygen, and I see the di. So again, once again, 2 nonmetals. So this is also covalent. Formula for carbon, that's C, tetrabromide, that's Br, 2 nonmetals. So this is covalent. Again, and then I need to remember all of my prefixes. So I'm going to use I'm going to put the prefix for the subscript, and then I'm going to put the element name. I'm doing this backwards. I'm going from there. I'm going to put the element symbol and then the subscript for its prefix. And repeat that again. The element symbol and the subscript. So in this case, nitrogen, the di is 2, oxygen, and there's the pent is 5. So N2O5. Sulfur, there is no prefix, thus it's an implied one of a prefix. Oxygen is for oxide. Remember, the covalent endings of the second element end in "ide." So I ignore the "ide" ending, and I'm really trying to identify which element are they talking about. In this case, ox is oxygen, and 2, SO2. Carbon, there is no prefix, so I don't have a subscript here. Bromine would be, I see bromine has been changed to "ide," but this is talking about bromine. Tetra is 4, so CBr4. So the covalent ones are much simpler. We will get that back in chapter 5 when we realize the structural formulas that we have to draw for the covalents can be significantly more work. Naming N2O3 and XCF2. Once again, first I want to identify, is it ionic, covalent, or an acid? So I see that N and O are both nonmetals. So this is covalent. Down here, I see xenon and fluorine are both nonmetals. So this is covalent also. And when I'm doing covalent, now I'll get ready back to that. So I put the element name and I put the prefix for its subscript in front. And then I put the second element name with the ending changed to "ide." And then I put the prefix for its subscript. Okay, so I'm going to put nitrogen. Its subscript is 2. The Greek prefix for that is di. I'm going to put oxygen, but I'm going to change the ending to "ide." And then I would put the prefix for 3 would be tri. Now, I kind of had to squeeze it all in there. Let's clean it up. Dinitrogen trioxide. Okay, Xe is xenon. You could put mono in front, but generally speaking, although it's not wrong to put mono in front, if it's a subscript of 1, we usually don't put a prefix. It's implied that it's 1. And then for the fluorine, I'll leave a space. And I'm going to change fluorine from INE to IDE. So it will be fluoride instead of fluorine. And the prefix for 2 is di, so xenon difluoride. Which of the following is named correctly? So again, I still want to type it. Is it ionic? Is it a covalent? Is it an acid? Because how can I possibly check if the naming is correct when they each have different naming mechanisms? So I look at the first one, I see it starts with H, so it is an acid. Let's just type them all, and then we'll go back and check the names. So this is sodium is a metal. So once I see it's got a metal in it, it has to be ionic. If I see a polyatomic or I see a metal, it's ionic. I also might have noticed HCO3 is a polyatomic, and I may have caught that. Lead is a metal. It's ionic. Sulfur and fluorine are both nonmetals. So it's covalent. And ICH it starts with H, so it is an acid. Okay, so let's handle these one at a time, changing colors. All right, for acids, this is a binary acid. Even, I don't need you to be experts at acid naming. You will get to be experts at acid naming in the second course in this series. But for binary acids, the structure is always hydro blank ic acid. So they all have that general structure. So binary means there's only two elements. And this one is binary. And so this is not correct. So no. So even if I don't know, so this actually would be hydrofluoric acid. Okay, here, let's look at this. So this is a type 1 metal. And kind of break it up into the cation and the anion. And this is a polyatomic. So I would want to check. So the type 1 metal is just its element name. And sodium is correct. That is the element name. And for if it's polyatomic, I want to check is HCO3 bicarbonate. And it is. So this one is correct. Okay, this is lead and oxygen. And when I look at here, I see that this is lead is a type 2 metal, which means I need to have the name and the charge in Roman numerals in parentheses. It is missing the charge. So this is wrong. Okay, so we've decided this is covalent. Remember, with the covalent, they need to have the name should have the correct prefixes. So, and it should have an "ide" ending. So let's look at this. So I see sulfur. This looks okay. There's one of them, so it doesn't need to have a prefix. That's okay. And then fluor, good. Ide is good. However, the correct prefix for 6 is hexa. So this is not correct. And then the last one, nitrous acid. Now these are tricky. Honestly, when it's an oxo acid, when it's not binary, we call these oxo acids because there are 3 elements and the third element is oxygen. So I need to identify the polyatomic ion. Sometimes for these, you just go look them up. I would almost recommend that you practice, just have a list of the very common strong acids and you just have them to look up against. But the way that we name them is we identify what is the polyatomic ion. So this is NO2 minus, which is called nitrite. If it is an ite, when we turn it into an acid, I change it to us. So nitrous acid. So actually, this is correct. I need to update my answers here. This is not okay. Na2HCO3. I was so busy focusing on is the name correct for that formula that I didn't do the due diligence to check the formula. And that is important. This is not an okay formula. If I look up sodium, sodium is a +1 ion, only ever a +1 ion. If I look up bicarbonate, HCO3 is only a -1 ion. Thus, NaHCO3 is valid, but Na2HCO3 would not be neutral because I have 2 charges with a +1 and one with a -1. Remember, this is sort of one of these with the -1. So this would be overall would be charged, and thus this is not an acceptable answer. So we get the idea of how to check these. But again, it's super clear that you know what kind of compound it is. And if it's an ionic compound, it is really important that you identify that whether the cation is a type 1 metal, a type 2 metal, or a polyatomic. And for the same thing for the anion, is it a non-metal anion or is it a polyatomic anion? You can't check the names if you don't know because the names depend on what kind of cation and what kind of anion. So watch out for those. Okay, now we get into the mathematical part of the chapter where we're talking about percent mass of a compound and the empirical formula. How could you get the empirical formula from the percent mass? So when we're doing percent mass, the idea is that the percent mass is the mass of the part, mass of X, whatever the part is, over the mass of the whole thing. And then, of course, times 100 to get it into percent. Okay, in this case, I need to do it for percent mass carbon because it says of all elements. Percent mass hydrogen, percent mass oxygen. So first, let's determine how much mass I have of carbon. If I have 1 mole, let's assume a 1 mole sample. In case if that's the case, it would be equals the mass of 2 moles carbon. And this one would have the mass of 4 moles hydrogen. And this would have the mass of 2 moles of oxygen. Well, I know the molar masses. So by assuming that I have 1 mole, I can use the molar masses. All right, so 2 moles of carbon would be 2 times 12.01 grams per mole. So 2 moles, the moles cancel, and I get 24.02 grams. For hydrogen, it's 4 mole times 1.01 grams per mole. Again, I'm looking these up on the periodic table, 4.04 grams. And for 2 moles times 15.99 grams per mole, the moles cancel, and I end up with 31.98 grams. Now, for the whole thing, I'm just going to total it up. It's made of these 3 masses. Let's add them all up. 24.02 plus 4.04 plus 31.98 equals 60.04. And so finally, I can say my percent mass carbon equals 24.02 over 60.04 times 100. And that gets me 40.00, actually 40.01. Percent mass hydrogen is 4.04 over 60.04 times 100. And that's 6.73. And percent mass oxygen is 31.98 over 60.04 times 100. And that's 53.26. Now, as a check, all 3 of these should add to 100. 40.01 plus 6.73 plus 53.26. Can't do it right on my calculator. 40.01 plus 6.73 plus 53.26. Okay, that worked. Equals 100. So that's good. Now, sometimes it's like 100.1 or 99.9 due to rounding differences. Sometimes it may be off by a tiny bit, but it should be very, very, very close to 100. This is sort of the reverse problem. What is the empirical formula of a compound that is 40.1% carbon, 6.6% hydrogen, and 53.3% oxygen? So in this case, I'm going to assume that I have a 100-gram sample. So 40.1% of 100 grams, I just multiply. Okay, well then that's 40.01 grams similar of carbon. Similarly, I could do the same thing and say I have 6.6 grams of hydrogen and 53.3 grams of oxygen. But I want to know, I'm trying to get to the mole ratio. So I need to go to moles, and then I have to divide by the smallest to get the mole ratio. So to get to moles, I'm going to divide each by its molar mass. So I know that carbon is 12.01 grams per mole. And I know that hydrogen is 1.01 grams per mole. And I know that oxygen is 15.99 grams per mole. Okay, so let's figure out what we get. 40.01 is 3.3313 moles of carbon. And 6.6 divided by 1.01, we get 6.5346 moles of hydrogen. I like to keep a whole bunch of numbers. It'll take care of itself later. So 53.3, I'm not ready for sig figs at this point. 3.33 moles of oxygen. Okay, at this point, I want to identify the smallest. Change colors. So this appears to be the smallest amount of moles. Therefore, I'm going to divide all of these by 3.3313. Divide by 3.3313. And this is going to be the ratio, mole ratio to carbon in this case, because carbon happened to be the smallest. Well, obviously, I'm dividing it by itself, so this is going to be 1. So it's a 1-to-1 ratio, obviously, because it is the same thing. So 6.5346 divided by 3.3313 is 1.96. That means 1.96 moles of hydrogen for every 1 mole of carbon. So I'm ratioing, I'm saying hydrogen, I have 1.96 hydrogens for every 1 carbon, right? And this one, 3.3333 divided by 3.3313, it's going to be very close to 1, and in fact it's 1.000. It does eventually, or maybe it's 1.001. But it's pretty darn close to 1. That's saying 1 mole of oxygen per 1 mole of carbon. So I can see that there's 1 carbon for every carbon. This is it's above 9. So in other words, if it's 0.9, I can round it up to the next whole number. Or if it is 0.1, I can round it down to the whole number, to the lower whole number. So if it was 1.86, I can't do that. If it's 1.76, 1.56, 1.46, 1.36, 1.26, if it's 1.16, I'm still kind of on the edge, but probably could round down. But if it's 1.06, I can round down. So it has to be really, really close to a whole number. But I won't get an exact whole number because of experimental conditions and rounding errors. So, but I can say that this is 2. Note that now that I have whole numbers, I can say this would be 1 carbon, 2 hydrogens, and 1 oxygen. 1 to 2 to 1. What you can make mistakes is that if this is not ending in 0.9 or 0.1 or 0.0, you cannot round it up or down. In those cases, then what I have to do is I have to try doubling all of them, then try tripling all of them, then try quadrupling all of them until all three are whole numbers. So this is now CH2O. Now, if you were paying attention, you might see that these were the answers we got on the last page. However, on the last page, it was not CH2O, it was C2H4O2. So it was a molecular formula. And now we see that this is the empirical formula that I would have gotten if I had done a mass analysis. Very similar problem, except this one gives me a little bit of extra. It is asking me for the molecular formula. So step one, I'm going to get the empirical formula like I just did in the last one. In step two, I'm going to say that the empirical molar mass I should say, sorry, the divided by, I messed it up. So it should be on top, the molecular molar mass divided by the empirical molar mass tells me the number of units of the empirical formula. So basically what I multiply every subscript of empirical formula by. Okay, step one, let's change colors so we can tell it apart. 26.7 grams. Again, I'll assume I have 100 grams. And then the percents become how many grams I have of each, because I want mass, not percentage. 2.2 grams of hydrogen, 71.1 grams of oxygen, the molar mass of carbon is 12.011, 1.008 grams hydrogen per mole of hydrogen, and 15.999 grams of oxygen per mole of oxygen. Okay, 27.6 divided by 12.011 equals 2.229. And 2.2 divided by 1.008 equals 2.183. Say 25. And 71.1 divided by 15.999 equals 4.444. That's how many moles of oxygen I have, moles of hydrogen I have, and moles of carbon I have. Again, I need to get to a mole ratio. Don't forget this step. A lot of people will work on these. I can't use these yet. I first need to ratio it to each other. The smallest number one is here, so I'm going to ratio it to this one. So I'm assuming that I have 1 mole of 1 hydrogen in this formula, and I'm looking at the rest. So I'm going to divide this one. Dividing it by itself will get 1. Dividing this one by 2.1825. I still have 4.444 on my calculator, so I'm going to do that one first. 2.1825. This number is 2.036. And 2.2229 divided by 2.1825 equals 1.015. So again, this is a 0. I can round down. So this is 1 to 1 to 2. So my empirical formula is CH. Wait, sorry, this should go down to 2. CHO2. With that, I can determine what the empirical molar mass is. So it'd be 12.011 plus 1.008 plus 2 times 15.999 equals, let's see what we get. 12.011 plus 1.008 plus 2 times 15.999. I get 45.017. That's how much, if the molecular formula was CHO2, the molecular molar mass would be 45.017. However, the molecular molar mass is 90.04 divided by the empirical molar mass, 45.017, which is 2.000. In other words, I have 2 units of CHO2 in this molecule, which means I'm going to double all of these subscripts. So C1 becomes C2, H1 becomes H2, O2 becomes O4. That's how I come up with the molecular formula once I know the empirical formula.